No? My name is Selim, Günay. I'm a project scientist here at Peer. So in this presentation, I'll be talking about the core aspects of hybrid simulation, including substructuring, integration methods, and simulation errors. This was just working. No, it's not. You're signing pedal. Okay, we had the magic touch. So, so this is the outline of my presentation. So I'll start with an introduction and talk about these aspects. And at the end, very briefly, I'll talk about, for 2 slides, about geographically distributed hybrid simulation and real-time hybrid simulation to complete the picture mainly. Okay, so starting in a really broad sense, what we do in laboratory testing in structural and earthquake engineering can be categorized into shaking table testing, quasi-static testing, and hybrid simulation. And hybrid simulation can be done on a shaking table or in a quasi-static manner. And as Professor Selim showed in his presentation, hybrid simulation can achieve the realistic nature of a shaking table test with a small increase in the cost of a quasi-static test. And obviously, this great achievement and efficiency did not happen overnight. And it required a lot of research, including 50 years of research on various different aspects of hybrid simulation. And what are these aspects? First, nature of the problem requires substructuring, and also the presence of experimental substructures in the domain require the use of special integration methods. We cannot use all the integration methods directly. And also the presence of a transfer system, the controllers and the actuators and so on, introduce simulation errors. And obviously it has been mentioned a couple of times in the previous talks. Rate-dependent materials require real-time hybrid simulation. And if we make use of multiple labs for different substructures, basically this extends the method to geographically distributed hybrid simulation. Okay, starting with the substructuring, as it has been shown in the previous talks, basically in hybrid simulation, the structure is divided into experimental and analytical substructures. And the analytical substructures are generally those that can be modeled with confidence. So we know what we are doing in terms of modeling, so we model them. On the other hand, experimental substructures are the ones that are difficult to model, and this could be due to various reasons, such as lack of prior data, complicated geometry, material highly inelastic behavior, and complicated boundary conditions, and so on. So actually here I'm showing an example from a bridge, from a highway bridge in Northern California, and according to Caltrans and Ashto design philosophy, the superstructure needs to remain elastic. So if we assume that the design is done correctly, the superstructure, including the deck and the girders and the cap beams, they remain elastic, so they can be modeled in the computer in a straightforward manner. On the other hand, the columns are the components that would sustain the damage, and therefore, due to the material nonlinearity, modeling of the columns may not be as straightforward as modeling an elastic component. So therefore, the columns are modeled as experimental structures in this example. So related to the analytical substructures, actually depending on your model, analytical substructure can vary between the case of no analytical substructure, where you model only mass and damping, to a case where you have an analytical substructure with many degrees of freedom. And the way that you divide your structure into its substructures and the boundary conditions between the analytical and experimental substructures basically define the experimental degrees of freedom, and also how these experimental degrees of freedom will be controlled. And actually in the next couple of slides I'll show some conceptual cases for different substructuring situations, and I'll go from the simple to the relatively complex cases. And in this set of slides, the red shows experimental and blue is analytical. So I start with a really simple case, a tested column with only translational mass modeled in the computer. Here is the basic case where we have only one translational degree of freedom and only one actuator is required basically to control this degree of freedom. In the case of a same column where we need to consider the mass moment of inertia, such as this column which has a huge mass and mass moment of inertia at the top, we basically have 2 degrees of freedom, and now we have the rotational degree of freedom included, and this can be controlled by 2 actuators configured in this position. If we have 2 columns tested in this configuration with 2 masses, translational masses, in the computer, again, we have 2 dynamic degrees of freedom, which are the experimental degrees of freedom, and basically we need 2 actuators to control these 2 degrees of freedom. And actually things slightly become complicated when we model one of the columns and when we test the other one. So in this case, the experimental column is the one at the bottom and the analytical one is the one at the top. And here we have these 2 degrees of freedom, the translational and the rotational, and we need the rotational here because of the moment transfer between the analytical column and the experimental. And basically same thing as the single column, these 2 degrees of freedom can be controlled with these 2 actuators. And actually the situation is even a bit more complex when the tested column is the one on the top and the analytical column is the one at the bottom, because in this case we have this translational degree of freedom plus another translational degree of freedom and the rotational degree of freedom because of the moment transfer again. And basically these can be controlled using 3 actuators which control the 3 degrees of freedom. And if we have the bottom structure instead of a column that would transfer moment, if we have a spring with no rotations, then we have 2 degrees of freedom and we don't have the rotational degree of freedom, and this can be actually controlled with only a single actuator because the column experiences damage due to the relative displacement between the top and bottom degrees of freedom. And in the case of a portal frame where we have one of the columns tested and the remaining in the computer, we again have 2 degrees of freedom, one translational and one rotational, and they can be controlled through this set of actuators. And in the case of frames, which are connected in series, one experimental and one analytical, that are connected to each other in series with these pin connections, then we again have 2 translational degrees of freedom, and actually these are the main dynamic degrees of freedom and the condensed dynamic degrees of freedom, which become the experimental degrees of freedom, and these can be controlled using 2 actuators. If the analytical frame is connected to the experimental frame through rigid moment connections, then we have the additional rotational degrees of freedom, and then these need to be controlled using 4 actuators in this configuration. Okay, so then this was about substructuring. So I'll move on with the integration methods. And as I mentioned in the beginning of my presentation, we cannot use all the integration methods in hybrid simulation, and the reason for that is mainly the experimental presence of the experimental simulation, experimental substructure, which I'll explain the reason in the next slide. But as an example, the most commonly used integration method, which is implicit Newmark, cannot be used in hybrid simulation. Okay, you don't need to know all those equations anyways. So, but what I'll mention is, so the implicit Newmark integration is basically based on a discretized equilibrium equation, which is this equation, and two difference equations where we define the displacement and velocity of the next time step in terms of other parameters. And here, just as a side note, the parameters gamma and beta define the variation of accelerations over a time step, and gamma 1 over 2 and beta 1 over 4 is the constant average acceleration over the time step, and this beta 1 over 6 is the linear acceleration. So when we combine these three equations, we end up with a nonlinear system of equations, and basically the nonlinearity comes from the resisting force, which is nonlinear as a function of displacement. And this nonlinear system of equations need to be solved. And the way to solve these set of equations is using iterative methods such as Newton-Raphson. And obviously, iterative methods, as the name mentions, they have iterations. And iterations are not good for hybrid simulation because of obvious reasons. And the first reason that iterations are not suitable is they may not converge at all. So you may be running a test, and at the middle of the test, if the iterations do not converge, you may not be able to finish the simulation with a demo specimen at the middle. So this should be obviously avoided. And the second reason is all the iterations result in artificial loading and unloading on the specimen, which are not part of the true dynamics. They are just as a result of the numerical computation, but they are physically applied on the specimen. So in the case of analytical substructure, all these iterations and the loading, unloading is not important on the analytical substruction because it doesn't have a memory, but everything that we apply to an experimental substructure affects it. And the third reason is mainly for real-time hybrid simulation. So if in the case of nonlinear uniform displacement increments between the iterations, there are velocity and acceleration oscillations which would result in incorrect force feedback and which would reduce the accuracy and reliability of the hybrid simulation. So therefore, in hybrid simulation, we use hybrid simulation compatible integrators. And these are three examples: explicit Newmark, operator splitting, and implicit Newmark integration with fixed number of iterations. The first two are those that do not require iterations. And the third one is a version of implicit Newmark integration modified for hybrid simulation. So I'll quickly talk about these. Explicit Newmark integration, I'm just showing this to show that the algorithm is pretty straightforward and it doesn't require iterations. So again, we don't need to know the equations, but this equation is used to compute the displacements for the next time step, and then these computed displacements are applied to experimental substructures to measure the corresponding resisting forces. On the analytical side, we get the resisting forces from the constitutive relations, and then eventually we obtain the resisting force vector. And this resisting force vector and other terms are used to obtain the compute accelerations, and then eventually you compute the velocities, which completes integration time step, and we are ready to move on with the next.
Just a quick note, if somebody is following the equations, each and represents a differentiation, a dot. The formatting is the error. So the double and is double dot. Okay. So that's the way
You need
I know that
to
computer.
install the equation editor in your computer.
We'll do it in the next break. Yeah.
This was the human error.
No mistake.
Because it doesn't have the equation editor. So this computer.
So and is a differentiation. So.
No, why don't, just this same slide, what is that px term? P sub x. Second line, last term.
P sub r.
P sub r is
sorry,
resisting force.
Yeah, what is P sub r?
The resisting force vector.
Is that the
Like
axial
in
or
the
the
case
lateral?
of an elastic case, you can compute it as k times the displacement.
Oh, I see, is that
Yeah,
part.
it's the resisting force.
For the physical displacement. Because you have a load cell.
Thank
So explicit Newmark basically becomes explicit by setting one of the parameters beta to 0, and in one of the nice things about the method is initial and tangent stiffness matrices are not required, and also iterations are not required, as I have shown. And therefore, because of these reasons, it's computationally very efficient. And one thing to highlight is this coefficient matrix that we use to solve the linear system of equations is constant during the solution because it contains the mass matrix and the damping matrix, which is generally constant. So we have this term constant. Therefore, to solve this linear system of equations, this coefficient matrix need to be factored only once, which actually results in a significant advantage in terms of computation time. And the method doesn't include any numerical damping. And it's a great method, but the only disadvantage is it's conditionally stable, and stability requirement is this represented with this equation. dt divided by Tn should be smaller than pi. So this is my pi. It's not incorrect. I can find a better one. So and yeah, actually here dt is the integration time step, and Tn is the period of the highest mode of the structure. And because of this reason, this stability requirement is not applicable to structures with massless degrees of freedom, such as frames where you don't have any mass moment of inertia in the nodes. These type of structures have zero period modes, and obviously they don't satisfy this equation. Therefore, explicit Newmark method cannot be used for these type of structures. And in the case that the stability condition is satisfied, I can probably say that this is the most suitable method for both real and slow real hybrid simulation. And the next one is the operator splitting method. Also, it doesn't require iterations. It consists of one predictor step and one corrector step. And just for the information, this eliminates the iterations by ignoring the acceleration term for the next time step in the displacement difference equation. And here we don't need tangent stiffness matrix in the coefficient matrix or anywhere else in the algorithm. And actually this is also a great advantage because it's generally difficult to identify the tangent stiffness matrix for experimental substructures, especially when it's multiple degrees of freedom. And also the method is computationally efficient, and similar to the case of explicit Newmark integration, the coefficient matrix here is constant during the solution and it needs to be factored only once. And this is unconditionally stable for softening response in the inelastic part, and this is generally the case for most of the structures, and therefore it's unconditionally stable for most structures. And also numerical damping is present, which you can use to reduce the effects of errors. And it's similar to explicit Newmark, it's quite suitable for slow and real-time hybrid simulation. So the third one that I want to highlight is implicit Newmark with fixed number of iterations. And basically this method uses a constant number of iterations. So you don't do any convergence checks. Let's say you say I'll do 10 iterations, and no matter what, I'll move on to the next time step after 10 iterations. So because of this reason, just to make sure that convergence is guaranteed, you need to determine the number of iterations with prior analysis so that you don't have a lot of errors due to any non-convergence issue. And this is also quite suitable for slow hybrid simulation, but it has restricted use in real-time hybrid simulation. And this is an example. So if we have an integration time step of 0.01 second, and if we have, let's say, 10 iterations, then each iteration needs to be physically completed in 1 millisecond, which may not be possible. So therefore, it has restricted usage in real-time hybrid simulation. Okay, so then
You need something?
No, I had some water. I couldn't find my water. So okay. So related to the simulation errors, since hybrid simulation is a combination of analytical and experimental simulations, also the errors from analytical and experimental simulations contribute to the method in a negative way. So these two errors here due to structural modeling and due to numerical methods are those that are common with any analytical simulation. And also we have the errors that are due to the presence of a control system, which are the experimental errors. So errors due to structural modeling, some examples are those due to the assumption of structural idealization in terms of discretization in time and space, and also things like using lumped masses instead of consistent mass matrices and so on. And one thing is obviously we model damping in hybrid simulation, and therefore, and always damping modeling is a challenge in structural engineering. So therefore, we accept any assumptions that we have in terms of modeling damping in hybrid simulation. And also, in certain cases, some artificial moments may be introduced when initial stiffness proportional damping is used, but this is common also in analytical simulation. And related to the errors due to numerical methods, as I mentioned, it is challenging to get the tangent stiffness matrix for an experimental substructure in the case of multiple degrees of freedom. So therefore, one solution to this is when you don't have this, you use the initial stiffness matrix for those integration methods that require the tangent stiffness matrix, and this may lead to errors. So if you use an integration method that doesn't need the tangent stiffness matrix, that's fine. And also, as I mentioned, because of these artificial loading and unloading cycles, experimental errors, also the simulation errors, increase with the number of iterations. And since higher modes are more stiff, they are more susceptible to error propagation than the lower modes, because any small error that you have leads to a bigger force error. So therefore, in these cases, numerical damping is desirable for suppressing higher modes, but caution should be exercised in this case that you should use enough numerical damping not to reduce the lower mode participation. And experimental errors, so in hybrid simulation, the basic step is you compute the displacement, and then you apply this to your specimen and measure the corresponding force. So reliability of hybrid simulation therefore depends on the accuracy of the measured force, measured resisting force. Therefore, any error that we have during the application of the displacement and measurement of the force is an experimental error, and it affects the hybrid simulation directly. And experimental errors can be divided into two: random errors and systematic errors. And random errors, basically, as the name says, they have no distinguishable pattern, and no specific physical effects can be anticipated. And examples is the electrical noise, or some rounding off in the analog to digital conversion. And generally, these do not introduce significant errors to hybrid simulation. And on the other hand, the systematic errors are important, and they may lead to error propagation and even numerical instability. And the examples of these are the measurement errors, the errors due to the hybrid simulation technique, and the servo-hydraulic closed control loop errors. The measurement errors are those that are in the measurement of the load cells and the displacement transducers, and these could be basically due to calibration errors or friction or slope in the attachments, or due to the analog to digital or digital to analog conversions. And related to the hybrid simulation technique, in the early stages of the method, the ramp and hold method was a method that was used widely, and basically in this application, during the computation duration, any actuator was held in position, and when the next displacement is computed, the actuators start to move to that target computed displacement, and here you measure the forces, and then again wait when the computation is going on, and the process continues like this. And the disadvantage of this is basically when you are doing the computation, you are waiting, right? And then depending on the material, this could lead to force relaxation, and which would lead to incorrect force feedback, which would make your hybrid simulation inaccurate. So to avoid this, as Dr. Yu mentioned, predictor corrector algorithms have been developed, and what these do is, instead of waiting during the hold stage, basically you move your actuators in a trajectory based on the previously computed displacements, which is called prediction stage. And when you compute the next displacement, you move the actuators to correct the position. And obviously this has less errors. So the control loop errors are those that are important in hybrid, and I'll quickly demonstrate this conceptually in this slide. So if we think that we have a linear specimen, a specimen with a linear force displacement relation, when we compute a displacement and apply this to our specimen through the transfer system, if the tuning is not perfect, this may lead to some overshoot. So we may apply the displacement larger than what it should be. In this case, the force that we will measure is larger than what it should be, but in the hybrid simulation algorithm, the displacement is still the computed displacement. So the displacement is still here. So what this does is it moves a point on the diagonal upwards, because now we have a different pair of displacement and force. And then this happens all the way in the loading part. In the unloading portion, any point moves downwards. So when we combine all these points, we obtain a hysteretic loop instead of a line. So in this case, in hybrid simulation, or the hybrid simulation observes a specimen that actually has a linear force displacement as a specimen with a hysteretic loop. and obviously this makes the computations incorrect. But on the interpretation side, this can be interpreted as increased damping. So we can say errors that lead to overshooting or lead in time result in increased damping. On the other side, time delay results in the same situation, but in this case, the direction of the loop is reversed, and that makes it more dangerous because this area under this curve is a negative area, so it corresponds to negative damping. You add energy to the system, and this can lead to instability.
Can you wrap it up here, Dr. Matt?
Sure. Okay, so then I have actually 3 slides, I guess, yes. Okay, so the methods to reduce the effects of errors is basically you need to do a good job in tuning, and if you don't have a sufficient controller, you need to use advanced control methods. And as I mentioned, integration methods with numerical damping are preferred, and error compensation methods can be used either, and there are various methods for this. Professor Bosan showed one method, and Dr. Yu showed another method. And we'll see another method later on during the shaking table demonstration. And so these are my last 2 slides. The geographically distributed hybrid simulation is actually a direct consequence of the substructuring. So instead of having different substructures in the same lab, if we have them in different labs, and even if the computation is done from some other location, all of these components can talk to each other through the internet, which makes geographically distributed hybrid simulation possible. And in the case of real-time hybrid simulation, the requirement is basically you need to apply the displacements in the rate, in their correct rates, and the loading rate basically need to be equal to the computed velocity. And in cases where rate effects are not important, where your resisting force doesn't depend on how fast you apply your loading, you can do slow hybrid simulation because that wouldn't change your resisting force and the hybrid simulation. But in cases where you have rate-dependent materials such as viscous dampers or friction pendulum isolators, you need to use real-time hybrid simulation. Otherwise, hybrid simulation will not be correct.
Thank you, Dr. Matt.